not too loud? No? Okay. In solar terrestrial and atmospheric physics. Okay. Using radar systems for this. It's an old organization. We existed since '76, doing radar since '81, and it's an international organization. So what EISCAT actually normally do is to provide instrumentation for scientists in our member countries. And just a little overview of what we have. We have one system on Svalbard with 2 big antennas, 32 and 42 meters. We have on Tromsø, we have a VHF transmitter, which is very, very big, 40 meters times 120 meters. So it's a football field in principle, and we can tilt it. We also have a UHF transmitter and receiver there. And we have, or rather we had antennas in Finland and Kiruna in Sweden. So actually Finland and Kiruna, Sweden, which was used for UHF receiving until mobile phones started dominating our frequencies, so we tuned them into VHF. But now they have been retired since a couple of years, and as late as last week, we gave away our keys to the Kiruna site, and later this year we will also lose our keys to the Sodankylä site, so these ones will not be used anymore. So, what is a radar? Radio detection and ranging. Transmit the radio signal towards something, and then we look at what comes back. That's as easy as it is, but what is data from an EISCAT receiver? Well, this is just a complicated thing to show that we are storing data as autocorrelation signals. So it goes through a set of frequency mixing and so on, but what we actually store is autocorrelation of what we have. And autocorrelation function is another way to express the frequency. In principle, it's a frequency spectrum that we save as a function of time. So why do I talk about the autocorrelation function to start with? It's all about the coherence time, and that's a time corresponding to the first zero crossing by the autocorrelation function, and this is important because the difference between coherent and incoherent scatter lies there. In coherent scatter, the coherence time is much longer than the time between the radar pulses, and incoherent scatter, it's much shorter than the time between radar pulses. And in the lower atmosphere, the coherence time is determined by turbulence, more or less, so it's much longer than 5 milliseconds, and in ionosphere, it's determined by the thermal fluctuation, so it's much shorter than 5 milliseconds. So in principle, if you have any time of measurements where you transmit more than one pulse in the ionosphere, we need to think about in the incoherent way. And normally a radar measurement, you sum over several pulses to minimize the variance. In incoherent scatter, you can sum the signal from many pulses first and then do the autocorrelation. But in coherent scatter, you cannot do that because the phase information is lost, so we do but the statistical information is still always there, so we first do the autocorrelation for each pulse and then some results. So here is simply, this is what the incoherent means in the EISCAT name, incoherent scatter radar. So what do we actually look at? We look at the free electrons, which requires an ionosphere. So we transmit the electric field, that's a radio wave from the radar at the origin in this system, and the electron is then accelerated due to the electric field. And when you have an accelerated electron, it will also transmit a signal, and we can receive that. And this process is called Thomson scattering. It's elastic scattering of electromagnetic radiation from charged particles, and it's non-relativistic, which for electrons means that it's less energetic than an X-ray. And then you can estimate the Thomson scattering cross-section from one single electron, and it's a very small number. So this is a good exercise for you then to see multiply over the ionosphere. If you look at our field of view is about half a degree. What would the total cross-section be for us if you look at the electrons? And I must say it's shockingly small. It's of the order of a coin. So that's why we, as I saw on the photos that I showed earlier, that our radar systems are very big. It's because we need to scream really loud to have something coming back, and we need to have big ears to listen to what comes back. In fact, it's 21 orders of magnitude difference between what we transmit and what we receive. So it's extremely small signals coming back and extremely loud signals sending out. So it's, in a sense, it's a very inefficient way of doing science. So we transmit lots of radio energy to the stars. So what comes back actually? So here I have a little discussion about the naive incoherent scatter spectrum. We assume that we get the signal back proportional to the electron density from the electrons up there, and we have Doppler spread because of temperature. And in the end we get something rather large width and rather low signal. So the first incoherent radar scatter radar system they built was in Arecibo, Puerto Rico, using this more or less naive approach. They built this 305 meters wide. But luckily the spectrum did not look as they predicted, so it had significantly narrower main feature and higher spectral peak, so it was much better to do. Much easier, so you don't need this big, you only need 30 meters, which is still a bit. So we need to think about what the electrons are really doing when they encounter our radio signals. We need to think about the collective effects because the ionosphere is a plasma. And now I show also equations that you have to memorize to be able to understand what I come to in the end. But this is one expression for how electrostatic fluctuations of the electric field in an isotropic three-dimensional collisionless plasma looks like. And in the denominator, we see this epsilon here, which is the plasma dielectric function. And if you remember something from fundamental plasma theory, it's that the dispersion relation for waves tend to be just having a zero of the dielectric function, which means that you get lots of the fluctuations are the power is focused rather sharply on zeros on the dielectric function. So we have peak in fluctuation spectrum near inherent wave modes, and we are a radar, so we provide the case and we see what omegas comes back. So electron density follows the electric field fluctuations when the waves are electrostatic. We are not looking at a single electron, of course, we look at the volume filled with electrons. So different parts experience different phases of the incoming radio signal, but we have constructive interference sometimes when the Bragg condition is satisfied. Which means that fluctuations of a specific wavelength propagating a specific direction are picked up by the radar system, and these have the enhancements at those specific frequencies that are inherent in the plasma. And these inherent wave modes that are moving around in the thermal plasma are ion acoustic waves, more or less sound waves in the plasma, we can say that, and we have the Langmuir waves, the plasma waves. So we expect peaks at these frequencies, and they are called ion lines and plasma lines. If you will hear that a lot if people are talking about incoherent scatter radars and the data. So then I just show an example of this incoherent scatter spectrum that we would get theoretically in a collisionless plasma. and no neutrals, just to make it simpler for my calculations. So we get 3 very clear spikes visible. So, but if I zoom in on the, y-axis, so we see this little bump here at the center, looking like that. This corresponds actually more or less perfectly to the naive approach. The only difference that has come after looking at the collective part is that we also have some other peaks. So now I zoom out on the y-axis and zoom in on the x-axis to look at the central peak. You see this, what is called the ion line, 50 times stronger and 300 times narrower than this continuous line. And it's from this one we get lots of the information that people are so proud of with the incoherent scatter radars. You can also look at the other peaks are plasma lines. It's very strong, but the frequency is very dependent on electron density, so they're quite hard to find in they fluctuate a lot due to the local electron density. So here we have the ion line, and from that one we get, the standard information we get is the ratio between the electron and ion temperature from the peak to valley relation of this. Relation between the bump and the valley. The ratio between the temperatures and ion mass is from the width of the spectrum, electron density from the total area under the spectrum, and the ion velocity from the frequency shift. So it's a Doppler shift. And then we tend to present our data in figures like this. Colorful, we have time on the x-axis and altitude on the y-axis, electron density, temperature for electrons, ion temperatures, and ion drift velocities. So this is a typical January day in Tromsø. So you have a little bit of sunshine in the middle of the day, not on the ground, of course, because it's still winter. Polar winter, but it's polar night, but it's at least up in the ionosphere, it's illuminated, so you get the UV there. And these data are stored also by EISCAT in level 3 data, and this is the data that you can access through the eScience Center, finally. So to note now, having receivers in 3 separate geographical locations, it's possible to measure the full vector velocity of plasma drift. So not only the line of sight, which is what you get from the Doppler shift, but you can get the whole thing. Temperatures and velocities are determined from spectral shape and Doppler shifts, but the density, it's from the actual height of the spectrum. And we may need extra calibration there because it depends on the antenna gain, and for example in Tromsø you have winters that are around 0 most of the time, and lots of snow, wet snow, so you change the antenna gain for filling the antennas with the wet snow. So for calibration purposes, EISCAT also has been operating dynasones. By using dynasones we can look at the maximum density and compare it to the F2, and then compare it to what we measure with the incoherent scatter radar, and then we can introduce this calibration constant, which is actually called magic constant in the literature, if you find that, the ISR magic constants. So now we're back to the list of things in the EISCAT eScience Center. So now you should understand why we have all the data types and what they are doing there. So to continue, we're searching for EISCAT radar data. It's called EISCAT Svalbard radar data, or in the Madrigal database, or UHF, VHF. So all these 5 points, in principle, what you get when you access it from the eScience Center is a link, takes you directly to a list containing all available EISCAT level 3 data obtained by the chosen radar system. And the reason why we have the vector data by itself is because it's not using one location, but it's, as I said, we're using one transmitter and 2 different receivers. We combine data from 3 sites. But of course, at some point when you click there, you need to enter name, email, and affiliation, which will be stored in a cookie before you can download the data. We've complained to the Americans who takes care of this Madrigal database that why would you need that, but they want it for some kind of statistics. So it should not be necessary, but it's there. So if you click on the link in the eScience Center, you get directly to the Madrigal interface. You see a list here of simply dates, start, and name, so you can click on the experiment you're interested in. And this time I was interested in 20th of March 2015, which is a couple of days after this big event, the St. Patrick's Storm. And then you get this select file, a list, the files, and they are a list with strange looking names, but the file with name beginning with MAD 6400 are the ones containing electron densities, temperatures, and ion drifts, and so the standard EISCAT data. So if we choose that one here, you can then, so as you see, like this, then you see that we have a couple of buttons: supplement files, download file, print file, view file info, cite this file. So in supplement files, there's a list of pre-made plots and other useful files describing the data. In download, you download the data, and in formats like HDF5, you can choose between HDF5, NET, CDF4, and ASCII. It's also possible to select which parameters to include and to filter the data before you download your data. Print file, you can display the contents, and view file info and cite this file, metadata about the data. If you want to cite the data, you get the, is it a DUI or, okay, I don't remember what kind of persistent identifier we use just in this case. So here I chose some supplement files, and I chose this file. And this file looks like this. So then I asked the students here, this is a couple of days after this big St. Patrick's Storm, 20th of March in 2015. There's one specific thing going on here around 10:15 UT, where the electron temperature suddenly drops very quickly, and the electron density also goes down a bit, so it seems like the recombination rate is going down. So if you know your history, what kind of event is this? It's a bit of a tricky one. It's a total eclipse of the sun. So this is what it looks like when you switch off the sun suddenly. Temperature first goes down and the electrons, and then, since they are not recombining, they are not ionizing continuously, it just slowly starts to go back. So this is the only good example we have of a solar eclipse, so that's why I showed it, and nobody, but the other plots are mostly for calibration plots and showing what has been going on. But looking at quick looks is not so fun in the long run, so we can also download the data, and you just click download, select as is, parameter files, and you get this selection of exactly which parameters you want to download, and that's quite a lot of parameters. But you can play around with this if you're interested. And then we go back to the Dynason data. What happens if you click on that button? Well, you get access to the Dynason data through the local EISCAT portal we have. The link in the eScience Center takes you to a login page, which I've heard people trying this, they get scared because the only thing they get is a login and nothing else, almost no information. So you need to be registered as a user to enter here. By the way, this is an interface from the 90s. So I don't know if anyone actually knows how it's actually done, so we cannot really change much. But you need to register as a user to enter. It's an immediate process. And please don't use a username, password, email combo that you use elsewhere, because everything is stored unencrypted. The only reason why we actually want this to be there is that you can restart your older sessions. So you should have a password an email that you actually use, so you can, if you need to be reminded of your password, which will be sent to you in unencrypted if you ask for it. Anyway, when you enter, you get a home page. Here I have the list of my previous searches. So it remembers your earlier requests. That's why we need to navigate. And then you can select station name and type of resource we're looking for. So here I look for EISCAT Tromsø ionogram. I get an ionogram for a specific time and date. This is an ionogram around the time of the eclipse, just to continue that theme. You can also plot time series rather directly. And of course, if you use the SQL query selection there of the type of data, you can download it as a ASCII, a list of ASCII numbers, so you can play around with yourself. So this is a way if you want to play more with the details. And that's the end of, I really rushed through this. So I can slow down on the summary, but I have some bonus slides later, so you don't have to stand up yet. Summary: EISCAT operates incoherent scatter radars, detailed ionospheric data from northernmost Scandinavia and Svalbard. So we are, of course, very limited in geography, what we can show, but we have very good coverage of the data in that part of the world. And the data are accessible through the PITHIA portal by clicking. So this is what I wanted to add on to this. PITHIA-NRF is one part of the activities that this training school is coming from. They also have a TNA program that I know several people, or at least some people in this room, has been accessing already. I have a poster on that door, on the outside of the door so you can look at it when you have coffee. But this is a chance for you to be able to use some instrumentations or models. And more important, you also get training to use those. So I understood that people were a bit confused about this continuous radio measurements in Czech Republic. If you contact the IAP, you can actually get a course, direct course, and play around with it to learn how it works. Ivan. And the deadline for this call is 31st of May, but you don't have to wait until the end of the deadline, because we do it continuously, looking through the applications. So we rather prefer you not to wait until the end of the deadline. And that's the end of my presentation.